Hi everyone, my name is Timo Walter and I'm a committer in the Apache Flink software project. In these videos I want to talk about Apache Flink, stream processing and software engineering topics in general. This video is about stream processing and what is actually stream processing. So many people think of some like video processing, some video signal processing when they hear stream processing for the first time. But stream processing also has a different meaning when we talk about event stream processing. So let's take a look what we consider as stream processing. Let's take a look at the stream processing landscape. So streams and event streams in particular can come in different flavors. You can process transactions like credit card transactions or order transactions. You can also process logs, for example, logs from some devices or logs from data centers, some IoT events, maybe also some interactions from users like click streams or scrolling streams or some other kind of button presses from users. When we talk stream processing, there are also various input and output systems involved. Usually there are messaging systems such as Apache Kafka, there are file systems such as S3, and there are also traditional databases such as, Oracle or MySQL, and there are key-value stores. Usually what you want to do with stream processing is you want to perform some kind of analytics. So for example, you want to get some insights into your real-time data. Sometimes you also just want to do some data integration, meaning you want to pipe data from A to B, from system A to system B. And sometimes you also want to do some ETL while doing that. So maybe you want to get rid of duplicates, or you want to join two streams together before you send them downstream. And then there is this whole category of event-driven applications. So what are event-driven applications? Those applications usually use time or state and form a more complicated business logic. So, for example, they usually use some if-then-else logic. So, for example, if event A comes in within 10 minutes, then send out this message. Or if event B is not followed by event C within 10 minutes, then send an alert. Or if event B doesn't come in time, send out a timeout message or something like that, or send out an email. So these are event-driven applications, and the output systems, the downstream systems are as diverse as the inputs. Again, we can have some messaging systems, some file systems, databases, and key-value stores. Or in case of event-driven applications, maybe you will also want to communicate to some other service, send out an email or a push notification. But interestingly, if you really think deep about all these kinds of inputs, transactions, logs, IoT events, and so on, you will quickly notice that actually all kind of data processing is always a kind of stream processing. And usually it's even processing a stream of changes. So you're basically processing change logs. And business data is usually a stream. It's just a difference whether the stream is bounded or unbounded. So like traditionally, when you run batch jobs or hourly jobs, you're cutting the stream into pieces. And then you are processing those pieces of the stream, right? So this allows you to process parts of the past, historical data. But good stream processors are actually able to process both. They are able to process unbounded streams, but they can also process bounded streams, because bounded streams are just a special case of streaming. So in a runtime, you can actually have some additional like specialized algorithms, and based on these algorithms, you can perform computations on historical data more performant. But in general, a stream processor is able to run analytics and other ETL pipelines on both bounded and unbounded streams. And the benefit of an unbounded stream is that you can also decide where you want to start processing the unbounded stream. So you can start in the now and process the future, but you can also start and bootstrap somewhere from the past, right? So you can say, okay, we start the stream processing applications maybe from 1 month in the past or so, and then we quickly process historical data, we process the now, and then we process future data. And as I said before, all this data can be considered as a stream of changes. So even if there is no change flag involved somewhere in your data, there is like every data point is a changelog entry, and this changelog entry has just insertion as the default changelog flag. So basically all data can be considered as a stream of changes. And when processing this stream of changes, interestingly, all stream processors can be categorized or need those 4 building blocks that are on this slide here. So first of all, you want to deal with streams, right? It's a stream processor, so there must be a way to deal with streams. But when there are streams involved, you also want to handle time, especially for these event-driven applications. And state is another very important component, because you might also want to buffer or cache data. And when you want to buffer and cache data, you also need to perform snapshots, not only of the state, but also maybe of the timers that you have set. So let's dive into each individual building blocks. Let's start with streams. Streams, first of all, allow you to pipe data from A to B. But sometimes you also want to perform parallel processing. So a stream processor should be able to distribute streams among multiple workers. And also the opposite direction. Sometimes you want to join 2 streams or multiple streams together. Sometimes there is also a main stream, and then there is an additional stream that has additional information. So you maybe want to enrich the main stream with this additional information. The other stream could also just be a control stream. So this control stream controls the behavior of an operator, and the mainstream can be controlled, or the processing of the mainstream can be controlled with this control stream. And of course, it is always possible that there is a bug in your logic. So ideally, what you want to do is also be able to replay streams, so process historical data and correct your bug. As I said, whenever we talk about streams and stream processing, there is always a time component. On one side, you want to make progress in time as quickly as possible. But on the other side, sometimes you need to wait for another event. And sometimes this event doesn't come in, so you also need timeouts. So there is always a trade-off between making progress, but also waiting and synchronizing maybe on a different stream and so on. And similar to replaying streams, if you want to correct a bug, or if you want to reprocess historical data, you want to fast forward your streams, and you also want to fast forward time. And that means it should also be possible to replay time and timer behavior. And then there is state. State always sounds like a very abstract concept, but a state can just be a Boolean flag. It can just be a number, a counter, or something like that. Usually in a stream processing topology, you want to be able to store some parts of data. This state store might be useful for just buffering data. For example, when joining, you want to buffer one of the input sites. But it can also be just a cache so that you don't have to perform a lookup into a database, which would be expensive. It can just be to store a machine learning model. And ideally, a state store should be able to handle also very large data in the orders of terabyte. And whenever you are storing data, you also have to think about expiration and for data protection reasons, right? So a good state store should be able also to define a TTL and also delete data if it has not been touched for a certain amount of time. And as I said earlier, whenever there is state involved and timers are also kind of a state, then you need to be able to perform snapshots of your stream processing applications. So snapshots, first of all, allow you to perform backups, also for fault tolerance reasons. But they also allow you to create different versions, to maybe fork your application, try out different logic, do some A/B testing with this different logic, allow you to time travel to an earlier point in time where the stream processing application maybe was behaving correctly. And it allows you to restore the whole topology at various point in time. So yeah, this should give you a rough estimate about how a stream processor works and how you can classify stream processors out there in the market. And yeah, the devil is in the details, and I will go more into the details in my next videos. Thank you.